I'd like to introduce Brian Ford. Professor Ford is head of the Department of the Built Environment at the University of Nottingham, and he will speak on what I think is proving to be a very germane topic of how to naturally ventilate tall buildings. Would you please welcome Professor Brian Ford?
Thank you very much. Before I kick off, I thought I'd just say I've come in from the UK. I understand that there are probably over 170 nationalities represented at this conference, which is amazing. When I left the UK, it was rather cold. It was bright but cold. But to my astonishment this morning, sitting in the big hall next door, I found myself shivering. I really was shivering. And I held my coat around myself, and actually it was something that Habiba al-Marashi, who was in the session just before lunch, commented on, that this hotel, like many, really overcools their buildings. And I'd like to do, with your indulgence, Chairman, I'd like to do a little straw poll and ask how many of you are just slightly too cool. Could I? That's a majority. Yeah, I think we're going to have the management down, and we'll engage them in a conversation. Anyway, to my talk, which is on natural ventilation of tall buildings. Those of you who were in that session just before lunch will have heard both Mike Bevan of Arup and Ken Yang refer to this as an issue. But as we are in Dubai, I couldn't resist pulling out a slide that I took on my last visit here of these wonderful wind towers, and it indicates that, of course, the natural ventilation of buildings is something that has been there in our tradition for a long, long while. But of course, the application to tall buildings poses its own design challenges. My talk is in 4 parts, and firstly I'm going to ask why we should consider natural ventilation for tall buildings. Ken Yang this morning indicated there were strong financial reasons, which I believe is the case. We'll look also at the energy aspects of it. Secondly, what are the principles and strategic options? Well, the principles are going to remain the same for natural ventilation of any building, but the strategic options are going to be slightly different, and it's really strategy, or 2 basic options, strategic options, that I'd like to explore with you. Thirdly, what are the further design implications? Because we can get the strategy, we can sort out a strategy, we can test the strategy, but actually if we don't then develop the design in detail and deliver that in detail, we're not going to have a successful building. And then fourthly, where are we going from here? What is the leading edge? So, firstly, why consider natural ventilation? This slide, or this table, compares the annual carbon dioxide emissions for 4 different office types. The naturally ventilated cellular building, a naturally ventilated open plan, and then 2 air-conditioned, standard office and a prestige office. We won't dwell on the detail of these figures, but I want to point out here that, and this data is for Northern European office buildings, all office buildings. This is not just tall buildings, this is all office buildings. It's actually a slide I borrowed from Spencer de Grey from Foster's. And he points out that the difference between a naturally ventilated open plan office and a prestige air-conditioned office can be a factor of 5, between 12 kilograms per square metre for the naturally ventilated office to 60. Now this is very significant indeed, and this is, to my mind, the primary reason in sustainability terms for looking at natural ventilation. What are the risks, though? What are the risks and opportunities? Well, on the downside, the driving forces, wind pressure and buoyancy pressures, can be very large indeed. And this, of course, can lead to problems of control. And so we need to look carefully at the big variation in pressure differences that might arise. Secondly, of course, adventitious leakage needs to be minimized, and in fact, of course, with there's been a drive towards tighter and tighter envelopes, and indeed, actually, with ventilated double skins, then this is further improving the air tightness of our outer envelope. Air tightness being desirable in combination with controlled access to natural ventilation. On the positive side, we can actually use the higher, greater wind pressures to our advantage. And at height, wind pressures are more predictable. There isn't the amount of turbulence, of course, that we experience at lower level in our cities. Similarly, buoyancy or stack forces can be very large indeed, and we need to control the flow pattern which is generated in this way. But this I believe, is both positive attributes. If we look at the basic forces, the basic distinction between wind and stack pressure. The wind pressure is directly proportional, and I'm sorry if I'm teaching you to suck eggs, but the wind pressure is directly proportional to the square of the velocity. So of course, if we just have a slight increase in the wind velocity, then we're going to have a significant increase in the pressure difference around the building. And as that wind speed increases further, then the pressure difference increases even further. So this is a significant aspect. And of course leads to a very much wider range of pressures around tall buildings than at low level. And this can, of course, exacerbate control problems. With regard to buoyancy on its own, then buoyancy pressure, of course, is directly proportional to temperature difference, but also height is significant. So buoyancy pressures can also become particularly large, particularly where the temperature difference acts over the whole height of the building. I'd now like to look at two distinct strategic approaches. Firstly, I'm going to look at isolated spaces, and this refers to the kind of dinner plate stacking that Ken Yang referred to just before lunch. And with isolated spaces, so firstly I'll look at isolated spaces, then I'm going to look at connected spaces, and I'll give an illustration of both. So with isolated spaces, if we take this diagram, with the single cells A and B, we know that we can achieve successful single-sided ventilation where the height to width of the room is about 2:1 or thereabouts. Whereas with cross-flow ventilation, as indicated in floors C and D, we can get successful cross-ventilation with a width to height of about 5:1 or thereabouts. Just as cross-flow can be induced by wind pressure, we can have successful ventilation in an open plan office of that kind, purely driven by buoyancy, and that's case E. So with isolated floors, what are the design implications? What are the advantages and disadvantages? Well, the principal advantage of the isolated floor approach is that each floor can be studied in isolation, and then replicated. And so this is greatly simplifies the analysis. The disadvantage, or a couple of disadvantages of the isolated floor, is that it can impose limits on the width to height ratio. So, and I've already referred to the commonly assumed ratio of width to height of equal to or less than 5 for cross-flow ventilation. But this implies that for a 10-storey building, the height, we'd have to limit the height to width to less than 2. But with a 50-storey building, this implies a height to width ratio of less than 10. With the isolated space, high wind pressures can, and I've referred to this before, can obviously be experienced, but while buoyancy pressures remain low. But these large differences between open areas required to achieve the flow rates under both wind and buoyancy alone can be problematic. So, and we'll have a look at some of this. So here is Ken Yang's Menaro Unno Tower, which he showed himself this morning. And I would say this is an example of an isolated floor strategy. It has wing walls to catch the wind, and it promotes cross-flow ventilation. And this is a really seminal building, I think, and I was very glad that Ken showed it this morning. I think it was completed in 1992, around about then, and it was very radical at the time. And I think the design process is very interesting, because from the strategy and the evolution of the floor plate, the design team then tested that strategy using CFD, and we see here illustrations of under both wind and buoyancy conditions. And then they developed the design in more detail, and as you can see in the diagram in the bottom left. So this process from strategy, testing the strategy, design development, is a crucial part of it. But what I feel is hugely important as well is that we revisit our buildings after they're completed. And post-occupancy evaluation, which is something that really developed in earnest in the UK in the 90s, has yielded a huge amount of useful information. And there was a study of the Umnau Tower back in about 2000, which did show significant variations in internal conditions under natural ventilation. And in fact, I think many of the floors, if not all of them, have been retrofitted with aircon. But we shouldn't see this as a negative result. I think rather we should learn from this and learn what has gone right, what could be improved. Because this was a radical departure, and in a climate like Kuala Lumpur's, radical indeed. I'd now like to turn to a second strategic alternative, and that is to propose a strategy of connected spaces. And in this diagram, and it could apply to it essentially implies a segmented approach for a tall building. But here we have a central atrium which promotes cross-flow ventilation under both wind and buoyancy. And indeed, in this configuration, wind and buoyancy act together, which is useful because, of course, in the isolated floor plate, they can act against each other. All right, I've got to speed up. But if height h is too great, and say we took 180 meters and a delta T of 20, then we get some very high stack pressures indeed. And here, if we assume that all the openings are the same area, then we did a quick calculation, it's about 150 pascals. So we can overcome this by using internal resistances and smaller openings, as in case B. I think I'm running short of time. This is in my paper. What I'm going to illustrate with this graph is that actually by the segmented approach, or using connected spaces in this way, we can even out the pressure differences throughout the height of the building and make this more predictable. The illustration I was going to give here is the Commerzbank, which is the well-known Foster building in, where is it? Frankfurt, thank you. Completed in '98, and again, a radical building of its time. Now, this is actually a mixed mode building, but I understand that from relatively recent reports, this building is naturally ventilated for about 70% of the year. And it adopts this segmented approach, where individual office space is then served from the sky courts and central atrium. I was going to touch on envelope design, which of course is fundamentally important, and the developing use of ventilated facades. This is an office building by Murphy Yarn, which some of you may be familiar with from Bonn. Again, naturally ventilated for much. Well, actually, naturally ventilated, yes, for much of the year. There are perimeter fan coil units to provide a bit of cooling in the summer and a bit of heating in the winter, but essentially the ventilation regime is naturally driven via the ventilated skin, the double skin, through the office spaces and out via the 9-story high sky gardens. So very quickly, and I will wrap up now, where are we going? Well, I think this experience is such that we are moving towards completely naturally ventilated towers, and indeed this last example from Guadalajara in Mexico is a wholly naturally ventilated building, no air conditioning at all. And to conclude, I would say that natural ventilation is viable for tall buildings, and it can lead to major carbon reductions. The basic driving mechanisms can give rise to high pressure differences, but we can make use of those. There are different strategies that have been identified for tall buildings, and we can use either the isolated or the connected space approach. And segmentation appears to be the least risky of strategies to limit pressure differences. Before I go, and I know I've run out of time, the reason for writing this paper is that David Etheridge, my colleague, and I from Nottingham, were co-authors of a guidance document for natural ventilation in the UK for non-domestic buildings, which was published in 2005 by CTBUH. But this guidance document entirely neglected the field of tall buildings, and we would very much like to explore both the theory, the state of the art, examples and post-occupancy evaluation studies where we've learnt what works and what doesn't work, and then to pull this together in a guidance document. And to this end, we've proposed a collaborative research project, and this is the commercial, we're looking for partners. So if anybody is interested in this as a study, please contact me. I've got a single sheet summary if you'd be interested. Thank you very much.